PHY314. And this is a question about a Riemann curvature tensor, so let's write it down. This is a question for people who like lots of indices. We're writing it down in terms of the Christoffel symbols and their first derivatives. So, part A is show that the Riemann curvature written above is antisymmetric under the interchange lambda swapped with nu. In other words, we want to show that R alpha sigma nu excuse me, lambda equals minus R alpha sigma lambda nu. So the way you do that is you just take that expression for Riemann curvature, and every time you see a lambda you write a nu instead, and every time you see a nu you write a lambda instead. So we get R alpha sigma nu lambda on the left equals partial gamma alpha nu sigma with respect to x lambda minus partial gamma alpha lambda sigma with respect to x nu plus gamma alpha lambda omega nu sigma minus gamma alpha nu omega gamma omega lambda sigma. Okay, I think I did everything right. Notice, however, that this term here with a minus sign appears here with a plus sign. And this term here with a plus sign appears here with a minus sign. Let's put some little minuses to accentuate that there's a sign change. So if you take this pair of terms and you swap the two indices, the pair of terms changes sign overall because both terms have a relative minus sign under here relative to the sign they had up here. And the same thing goes for the first two terms. So if you take this term in the box, it's the same thing as this term down here, but with a minus sign, and similarly for this term, it's the same as this term down here with a minus sign. So that proves the assertion, because every term that appears in the top curvature symbol appears in the bottom curvature symbol but with a relative minus sign. Therefore it's true that R alpha sigma nu lambda equals minus R alpha sigma lambda nu. That's the first part. Well, fiddly is what I'd say about this question. It's a little bit fiddly, but it's not actually terribly hard. And the gift marks are in the next section, as long as you know a little bit about metric coefficients, and this is something we've touched upon before. So the next part says, show that in a freely falling, in a locally inertial frame, freely falling, all that means when I say it is that locally, up to corrections of order displacement squared, the metric is minus 1, 1, 1, 1. Okay? So if that's true, so locally inertial frame, the first derivatives of the metric coefficients are all zero. So I give you the important piece of information, which I was just about to say, is that if you take d by dx anything of g mu nu, you get naught where that flat space touches the curved space-time. So if that's true, what does it say about this expression? Well, you may or may not know that there's an expression for the metric curve, for the Christoffel symbols, in terms of the metric coefficients and their first derivative. So for example, if we take this one, gamma alpha nu omega, that's equal to g alpha, let's choose kappa, over 2 times the partial derivative of g nu kappa with respect to x omega minus plus the partial derivative of g omega kappa with respect to x nu plus partial derivative of g nu omega with respect to x kappa. So that's the expression. It was on last year's formula sheet. Okay, so as I said before, this formula is on last year's formula sheet. If you need it this time, I will supply it in the exam paper. It's not on this year's formula sheet. But for this question, you've been told that the first derivatives of metric coefficients with respect to any displacement coefficient are all zero in inertial frame. And because this bracket just contains first derivatives, this implies that at the point where the flat sort of tangent space where the metric is minus 1, 1, 1, 1 touches the curved space-time, these Christoffel symbols must all be zero. They're not zero everywhere. They differ from zero, slightly displaced from the point where the inertial frame touches the curved space, but they differ from a very small amount, proportionally to the displacement squared from the point of the tangent space touching the curved space. So if these are all zero, then these terms 3 and 4 in the Riemann curvature tensor are naught, because that's all they contain, is just Christoffel symbols, and you're left with the residual, which is the two first terms. These are not necessarily zero, because the second derivatives of the metric coefficients with respect to displacements are not zero. It's only the first derivatives that are zero, and these terms here, it turns out, have such second derivatives in them. So then they don't vanish, so you're left with them. So that proves the assertion of part B, and you get 2 marks for that, which I think is pretty generous. But you do have to know some stuff. Okay, so that's part B. Now for part C is a bit more interesting. You're told to show that a combination of 4 terms, all of which have second derivatives of metric coefficients in them, is an expression for the curvature tensor. So what you have to do here, and this is true again carrying on in the inertial space, so what you have to do here is start with this expression for the curvature tensor and put in the expression for the Christoffel symbol and actually do the derivative. Now this sounds like it's a pain, and it actually is a little bit of a pain, but if you keep calm, what is what we've got is R alpha sigma lambda nu equals the partial derivative with respect to x nu of gamma alpha lambda sigma. But gamma alpha lambda sigma is g alpha kappa over 2 times the partial derivative of g lambda kappa with respect to x sigma plus partial derivative of g sigma kappa with respect to x lambda minus the partial derivative of g lambda sigma with respect to x kappa. That's a lot of stuff. And then minus d by dx lambda of g alpha kappa over 2 partial derivative of g nu kappa with respect to x sigma plus partial derivative of g sigma kappa with respect to x nu minus partial derivative of g nu sigma with respect to x kappa. Okay, so there are 2 terms, each of which has quite a complicated partial derivative in. Now it looks like it's going to be horrible because each of these is going to be subject to the product rule, but fortunately half the terms go away, because if you ever have to differentiate the g out front, you've got a first derivative of metric tensor. In inertial frame that goes to 0. So this guy never gets differentiated. It does, but when it does it goes to 0, so you just pull it out as a common factor, and the same term appears in the second line as well, so you pull it out there too. And so all you're left with is taking derivatives with respect to x of these g's, which is going to give you second derivatives of g's, which is what you want in your answer. And the only thing you have to find is 2 of these terms that cancel with each other, and then you're left with 4 terms over, which is what you've got in the answer. So you can already see, just by looking at this, that it's going okay. So let's remain calm, erase this stuff, because we've already gone through all this, and then just do what we said. First, factor out the upper G alpha kappa over 2. So you have R alpha sigma nu lambda equals G alpha kappa over 2 times, right, the second derivative of G lambda kappa with respect to x nu and with x sigma as well, because we've already got the x sigma, plus the second derivative of G sigma kappa with respect to x nu, and then we've got x lambda, minus the second derivative of G lambda sigma with respect to x nu and x kappa. Right, that's the first 3 terms. And then we have minus the second derivative of G nu kappa with respect to x lambda. Notice that we've switched to an x lambda here, and we've got an x sigma left over, minus d squared G sigma kappa with respect to x lambda, and there's an x nu underneath from before, and then there's a minus sign here, but it cancels with the minus sign here to give you a plus, so you get a plus second derivative of G nu sigma with respect to x lambda and x kappa. Okay, that's all of them. Now, do any of these terms cancel? These two do. There's a plus sign and a minus sign, so the middle terms go away, and exploiting the fact that the metric components are symmetric, so I will swap some of them here to make it match the answer on the sheet. And whenever I swap them, it's fine, because you can interchange the 2 indices on the metric coefficient, and it makes no difference. You get G alpha kappa over 2 d squared G kappa lambda, that's that term, with respect to x sigma x nu. I've swapped the 2 derivatives, but that's all right because the derivatives are interchangeable. And then minus d squared G lambda sigma lambda with respect to dx kappa dx nu, and then that's that term, and then we have minus d squared G nu kappa with respect to dx sigma dx lambda plus d squared G nu sigma with respect to dx kappa dx lambda. And that is what you were asked to show in part C. So yes, it's fairly disgusting, but if you keep your head, all it is index manipulation, and not that complicated index manipulation at that. Right, for part D, you're asked to find an expression for a thing that has the same letter symbol R, but instead of having an upstairs alpha, it's got a downstairs omega. So to do that, you want to bring this this alpha down and replace it with an omega. So the way you do that is you do G, you multiply by G omega alpha, and then when you multiply that by R upper alpha sigma nu lambda, it has the effect of lowering the alpha and turning it into an omega, so that gives you what you've got here, which is R sub omega sigma nu lambda. Okay, and you have to do the same thing to the other side, of course, and on the other side what you get is G sub omega alpha times G super alpha kappa over 2 times the contents of the bracket, which is the same as it was up here. But this combination here of the 2 G's, if you remember from the notes, is a delta function between the unsummed indices kappa and omega, and then you multiply that by the big bracket, and then there's a 1 over 2 there we haven't lost. What this says is go through the bracket and replace all the kappas by omegas, right? So we end up with R omega sigma nu lambda equals, there's no G anymore, it's gone, it's just a half, right? And the delta's going to move into this bracket, and its function is to replace all the kappas in there by omegas. So when we do that, you end up with the expression that was asked for. Okay, so that sorts that one out. Okay, that's the expression in part D. Now in part E, you're asked what the symmetry of this tensor here, the rank 04 Riemann curvature tensor. This is clearly rank 04 because it's got 0 upstairs indices and lower 4 indices, and we know it's a tensor because that was, and we've lowered with the metric, which we always can. So it wants to know what happens when you interchange omega and sigma. Well, all you do is you do the same thing you did in part A. You just take this expression and swap the omegas and sigmas and see what happens. And it turns out that again, the plus terms swap with the minus terms. So if you do that and study it using the same method I just gave you for part A, you'll discover that R omega sigma lambda nu equals minus R omega sigma nu lambda. It's another case of a pair of components of this thing being related by a minus sign. It's antisymmetric. Okay, so that's question 5. I do wish you all the best of luck for the exam tomorrow, and I will, well, I don't know, I'll look forward to marking it, as much as lecturers usually look forward to marking things. And thank you for being an attentive class, and I hope you have a good holiday. I think I probably am most of your last exam, so do get yourself a break over the summer, and I'll see some of you next year. Bye.